Hi everyone, this is the syllabus for module 6 and it covers two major topics, stability of finite slopes and compaction of soils. So let's start our 6th module. What is a slope? If you're talking about an earth surface, what is a slope? So it is an unsupported inclined surface of soil mass and it can be either natural or man-made. So as a civil engineer, what are the various type of slopes that we encounter? So you can see the figure here. So in a highway, if you want to make a highway, you have to raise the soil from the existing level to the required height. So you have to put some earth and make it into a firm surface, so it will be having slopes on two sides. So we have to take care of this. And also if you are going for a railway track, if you are making a railway track, you have to lift the lift the ground surface in order to lay the track. So there also comes the slope. And if you are going to a canal, cross section of a canal, if you are observing it, you can see slopes. The embankments of the canal is made and it is having slopes on both sides. And about an earth dam, if you are making a dam which is resisting the forces by its own weight, it will be massive, and if you are using the material soil for making the dam, you can see slope is obvious. So these are the kind of slopes that we encounter in a civil engineering project. So there comes the need of understanding or stability of this type of slopes. So earth slopes or embankments are commonly required for railway formations, highway embankments, earth dams, canal banks, river training works, etc. And how should we consider this slope, or how to design this slope? The steepest slopes which are stable and safe should be provided. So this is the demand, because if the slope gets very steeper, it will fail. So and if the slope is somewhat steep, you have to have only less material to make it. So this is where the challenge lies. We have to make it stable and as well as safe to be economical. So we have to analyze the safety of a slope. And if what happens if the slope fails? Failure of a slope may lead to loss of life and property. If you are making a road like this, or if you are making a earth dam like this, if the slope fails, it will cause the loss of life and also loss to property. So the stability of the proposed slopes should be checked. Now the slopes can be of two types: infinite slope and finite slope. So what is the difference between these two? If a slope represents the boundary surface of a semi-infinite soil mass, and if the properties for all the identical depths below the surface are constant, then it is called an infinite slope. So the mass should be a semi-infinite type and the properties should be identical for all the depths. So such a case is an infinite slope. And if the slope is of limited extent, if the dimension, that is the sloping portion, is of limited extent, then it is called a finite slope. So what is an example for a finite slope? There are many: the inclined faces of earth dams, embankments, excavations, all these are coming under finite slopes because these are very limited. The extent is very limited, so such a slope is called finite slope. So we are concerned about the finite slopes. Stability analysis of such slopes is of vital importance to the geotechnical engineering profession. Slopes may be man-made or natural, and if a slope fails, it brings damage to life and property. So the slopes will be having an inherent tendency to attain a more stable configuration. And if a slope is having only the tendency to move, it has not moved yet, then it can be taken as an instability. The slope is very unstable, it has not moved yet. It has a tendency to move. And if actual movement occurs, then it is a slope failure. And a failure of an earth slope involves a slide. So what is a slide? It is a downward and outward movement of the entire mass of the soil that is participating in the failure. So the soil mass will be moving downward and outward, and a failure happens. So this failure can occur slowly, or it can be a sudden failure. So what are the various types of slope failures? So we can see in detail. So there are 5 numbers, different types. They are rotational failure, translational failure, compound failure, wedge failure, and some other types too. So coming to the first one, rotational failure. So what happens in a rotational failure? The failure occurs by rotation along a slip surface, and there will be downward and outward movement of soil mass. So the slip surface is the surface through which the failure happens. So the slip surface can be circular for homogeneous soils and non-circular for non-homogeneous soils. And again, this type of failure is divided into 3 types, and they are toe failure, slope failure, and base failure. So just look at the figures: toe failure, slope failure, and base failure. So what is the difference between these 3? Toe failure. In this type, failure occurs along the surface that passes through the toe. So this is the toe of this particular slope. So which is the slope surface? This is a horizontal layer, and this is a sloping layer or the sloping surface, and again a horizontal layer. So this is our slope here. So the slope surface at the downward point is the toe. So in toe failure, the failure occurs along the surface that passes through the toe, and these are the most common type of failure that happens. And what is a slope failure? In this type, failure occurs along the surface that intersects the slope above the toe. So somewhere above the toe, this failure surface will be meeting, and this is a slope failure. That means along the slope it is happening. And what is the base failure? In this type, failure surface passes below the toe. So look at the figure. Below the toe, the failure surface is coming, and this occurs when a weak stratum lies beneath the toe. And you can see all 3 in just one figure shown here. So you have to slightly rearrange it, like slope failure, surface is meeting the slope, and toe failure. This is the toe, which is a sloping surface here. This is the sloping surface, and it is meeting the toe. If the failure surface or the slip surface is meeting the toe, it is a toe failure. And if the failure surface is meeting somewhere in the slope, along the slope, it is a slope failure. And if it is happening below the toe, then it is a base failure. And one more thing is the depth factor. If h is the height of slope and dh is the depth of lowest point of failure surface, then d is called depth factor. So if you are considering the base failure in this figure, if h is the height of slope, isn't it? This is the height of slope. This is the sloping surface. So h is the height of slope. And if dh is the depth of lowest point of failure surface. So this is the failure surface in a base failure. So this is the lowest point. If you are considering the depth of lowest point from here, it is dh. Then d is called the depth factor. Now coming to the second type of failure, which is translational failure. So this occurs in an infinite slope along a long failure surface, and that failure surface will be parallel to the slope. So this is the slope here, and this is the failure surface, and will be very long, and this failure surface will be parallel to the slope. And this shape of the failure surface will be influenced by the presence of any hard stratum at a shallow depth. So this is a shallow depth, and there is suppose this is a hard stratum here, so it will be reaching the the failure surface will be reaching the hard stratum like this. So this shape of the failure surface is determined by the presence of a hard stratum here. And this may also occur along slopes of layered materials. Now coming to the third type of failure, which is compound failure. It's a combination of rotational slip and translational slip. And the failure surface is curved at two ends and plane in the middle portion. And this is generally occurring when a hard stratum exists at a considerable depth below the toe. Below the toe, at a greater depth, if a hard stratum exists, then it can have a compound failure. There is a chance for a compound failure. Now the fourth one is wedge failure or plane failure, or it is also known as block failure. So a failure along an inclined plane is known as a wedge failure. It occurs when distinct blocks and wedges of the soil mass become separated. So this is the plane surface and this is the plane of weakness. So a wedge portion is being displaced, or a wedge portion, the slope failure is occurring by the movement of a wedge portion. It is similar to translational failure, which occur in infinite slopes, but this type of failure may occur even in a finite slope consisting of two different materials, or in a homogeneous slope having cracks, fissures or joints, or similar plane of weakness. So if there is a plane of weakness in a finite slope which is having homogeneous material, then this type of failure may occur. And what are the other types? In addition to the above four types, there may be some other complex type of failures like spreads and flows. So we need not bother much about such other failures. Mainly we have to study the main four type of slope failures. What might be the reason for such a slope failure? We shall see what is the reason for failure of slopes. So the first one is gravitational forces. So how this gravitational force can cause a slope failure? So what is a slope actually? It is the inclined surface of soil mass. So what about the mass of soil? If the soil is very heavy, and if it cannot take that slope, it cannot withstand that steepness, it will be attaining some stable configuration. So if the weight is more, then that is a reason, gravitational forces. So it can cause a slope failure. The next is force is due to seepage of water in the soil mass. So there will be water seeping through the soil mass, and if it is more, and the force due to the water, seepage water will be more, and this will cause a slope failure. Then disintegration, and it is very progressive, the disintegration of the structure of soil mass. It will be another reason for slope failure. And also if somebody is excavating near the base of the slope, it will cause the failure of slope. So these are the chief reasons for earth slope failure. And you might have seen slope failures related to landslides, isn't it? Landslide is a slope failure. So what happens, or what is causing such a landslide? Maybe due to some earthquake. So in areas of seismic activity, earthquake forces may also be causing the instability along the slopes, and it may cause slope failures. Now these are the major reasons for slope failures. Now how it is happening? How it is happening? So the some forces are causing instability along the slope, and these forces can be called as actuating forces. So some force is causing instability, so the slope will be trying to resist it. So it will be trying to resist the deformation cost, or this trying to resist the slope failure. So there will be some stress being induced inside throughout the soil mass, and if the shearing resistance, or that resistance, if it is very less, then compared to the shearing force that is occurring, failure will occur along the slip surface. So the shearing resistance is mainly derived from the shear strength. So the soil will be having some shear strength and will be offering the resistance based on the stress acting. Stress means in the sense the shearing force acting on that surface. So, and also some natural factors such as roots, plant roots can also contribute, but we'll focus on the shear strength of soil, and we have to guarantee that. Then what are the factors? So in short, what are the factors leading to failure of slopes? So there may be some factors that cause an increase in shear stress. If the shear stress or if the force is more, then if the shear force is more, it will lead to failure of slopes. So what are the factors that cause such an increase? Weight of water causing saturation of soil. So if there is more weight of water inside soil mass and if it is saturated, then surcharge load. So what do you mean by surcharge load? Maybe some extra load coming over the slope. If you're making a house along a slopey surface or near the slope on a hillside, if you're making a house, you have to check whether the slope is stable or not. If you're giving some extra load of your house on that slope, so that may be taken as a surcharge load. Then seepage pressure and steepening of slopes by excavation or natural erosion. So natural erosion is also playing a part. If due to natural erosion, if the slope is getting steepened, it is causing, it is a factor that may lead to failure. And so the first one is increase in shear stress. What are the factors that cause increase in shear stress? Again, some of the factors can decrease the shear strength of soil. So the shear strength of soil is giving the resistance, helping the soil to give to resist that forces. So if some factors are causing a decrease in the shear strength of soil, that also will lead to failure of slopes. Again, that is increase in water content and pore water pressure, weathering, then shock or cyclic loads. Such factors will be decreasing the shear strength of soil. And most of the natural slope failures occur during rainy seasons. So in this rainy season, the presence of water is there. That will be increasing the stress and also causing a decrease of the strength of soil. So most failures, slope failures occur during rainy season. So what are the slope stability problems in soils? So you can observe the figure. Natural slope, there may be a stability problem in such a soil. Then cut slopes, if you are cutting it along the slope, if you have made some cuts along the slope, that is a that may bring a stability problem. So which are the areas that is where we expect stability problems? That is what focus here. So open excavations. So this excavation here, it is open, so it has a tendency to come down. Then these arrows are showing the probable direction of failure. And in an earth dam, what is the failure type? Then embankment over poor soil. If this is a poor soil and if you're giving some embankment means just a rise in the level of you have made it into a higher level. Embankment over the poor soil. There is a tendency for slope failure. And side hill fill. If this is a natural hill and if you are filling along the side of that, it has a tendency to come down. Then waterfront structures near water. So it has a tendency. This is a water level shown here. So water frontage structures have a tendency to fail along this type of surfaces. So these are the expected problems, stability problems in soils, and mathematical stability analysis is feasible for such problems. So we have to analyze the stability and predict the behavior. So we are stepping into the basis of stability analysis. How to analyze the stability of a finite slope. So most commonly it is done based on limiting equilibrium approach. So what is this approach? In this method, it is assumed that the soil is at the verge of failure along an assumed or non-failure surface. Limiting equilibrium approach. In this, we are assuming that the soil is about to fail, and we are assuming a failure surface, or it can be a known failure surface. And the shearing resistance required to maintain this equilibrium condition, we'll compare it with the available shear strength of soil. The soil will be having some shear strength, and what is the shear resistance required to maintain a limiting equilibrium? That is, the slope is at the verge of failure. The slope is about to fail. So to maintain that limiting equilibrium, the extreme equilibrium condition, to maintain that limiting equilibrium condition, what is the shear resistance? What is the resistance to be given? And what is the available shear strength of that soil? We'll compare it. Then the ratio of the available shear strength to the mobilized shearing resistance. This is the average factor of safety along that particular slip surface. So we have to find out what is the factor of safety. So we have to find out what is the factor of safety. So suppose we are applying some load on a structure. The stresses will be developing. And if you are increasing the load, what happens? The stresses inside will be increasing. And it continues, and the stress inside will reach the maximum, and the material, and later if the load goes up, then the material cannot take more load, and it will fail. So how much is the stress developed? That means that much resistance is offered to the deformation, to prevent the deformation. So it is having some strength, and some strength is being used every time to offer some resistance, that is induced as stresses. So what do you mean by this mobilized shear strength or mobilized shearing resistance? What is the meaning of that? So shear strength, maximum shear strength, or the available shear strength means how much is the shear strength available for that soil. Then mobilized shear strength or mobilized shear resistance means how much of that strength is actually used to resist. Clear? So we will take the ratio of this, and that is called factor of safety. So this is the basis of stability analysis. And what are the different steps? The failure or slip of finite slopes occurs along a surface which is a curve. So you observe here, this is the existing slope. This is the existing slope, and the failure along a surface. So this is a curved surface, and it is passing through the top. And in stability computations, the curve representing the real surface of sliding is usually replaced by an arc of a circle. So all these processes will be very tough if you are going for high accuracy. So instead of considering this as a curve, we will be taking this as an arc of a circle. So in stability computations, the curve representing the real surface will be usually replaced by an arc of a circle. And stability analysis of finite slopes involves the following steps. We will assume a possible slip surface, we will study the equilibrium of forces acting on the surface, and we will repeat the process until the worst slip surface is found. So the major thing is, it is based on limiting equilibrium approach, and we are assuming that the soil is about to fail, at the verge of failure along an assumed or non-failure surface, and we'll find out how much is the shearing resistance required to maintain a limiting equilibrium condition, and it is compared with the available shear strength, and we'll take the ratio, that is a factor of safety. Let's see what is the factor of safety in detail. So in the analysis, the resultant of all the actuating forces, the forces that are trying to cause failure, is called actuating force. So the resultant of all actuating forces is determined, and we will have an estimate of the available shear strength. So we know what are the forces, the resultant force which is trying to cause a failure, and we know the available shear strength of that soil. then factor of safety can be easily determined. So in this context, we have to come across three different definitions for factor of safety. So factor of safety with respect to shear strength, factor of safety with respect to cohesion, and factor of safety with respect to friction. So we shall see what are this in detail. So factor of safety with respect to shear strength, Fs. What is it? It is defined as a ratio of shear strength to the shear stress along the surface of failure. So it can be mathematically represented as Fs, factor of safety with respect to shear strength. Fs is equal to ratio of shear strength S to shear stress along the surface of failure. Fs is equal to S divided by tau m. And Fs and S is how we denote shear strength of soil. And what is this tau m? It is mobilized shear strength. Mobilized shear strength, I had explained it before. So the soil is having some shear strength which is available. We can use it to resist the deformation when some load is acting or when the slope is about to fail. Resist that. So how much is being used? That is based on the shear force acting at every stage, isn't it? Some shear stress is being developed, so that how much stress is being developed. So based on that, some amount has to be used to resist it. So that is what we call mobilized shear strength. So it is the amount of strength that is actually used to resist the failure. So that will be equal to the applied shear stress. Clear? Now the fourth one is wedge failure or plane failure, or it is also known as block failure. So a failure along an inclined plane is known as a wedge failure. It occurs when distinct blocks and wedges of the soil mass become separated. So this is the plane surface and this is the plane of weakness. So a wedge portion is being displaced, or a wedge portion, the slope failure is occurring by the movement of a wedge portion. It is similar to translational failure which occur in infinite slopes, but this type of failure may occur even in a finite slope consisting of two different materials, or in a homogeneous slope having cracks, fissures or joints, or similar plane of weakness. So if there is a plane of weakness in a finite slope which is having homogeneous material, then this type of failure may occur. And what are the other types? In addition to the above four types, there may be some other complex type of failures like spreads and flows. So we need not bother much about such other failures. Mainly we have to study the main four type of slope failures. So here is a statement: factor of safety with respect to cohesion and that with respect to angle of shearing resistance are equal to the factor of safety with respect to shear strength. So we have to prove Fs is equal to Fc is equal to Fi. So this was asked in a university question paper, so you just note down this. So here is the proof. We shall start with Fs value, factor of safety with respect to shear strength. Fs is equal to S divided by tau m. So S is shear strength and tau m is the mobilized shear strength. So this can be written in terms of cohesion intercept and angle of shearing resistance. So we are replacing this S and tau m in terms of C and phi. So we know that S is equal to shear strength, and shear strength can be represented as C plus sigma bar tan phi. This is the equation. This comes in the fourth module. So S is equal to C plus sigma bar tan phi. Again, tau m is also the shear strength, mobilized shear strength. So you can write in terms of m. You can represent it as mobilized using the letter m. So in the same form you can represent tau m is equal to Cm plus sigma bar tan phi m. So Fs can be written like this, and we can bring this Fs down and this term to the side. So C divided by Fs plus sigma bar tan phi divided by Fs is equal to this one, Cm plus sigma bar tan phi m. And if you compare, you understand, C divided by Fs is equal to Cm. And sigma bar tan phi divided by Fs is equal to sigma bar tan phi m. If you strike off this sigma bar common term, you can understand tan phi m is equal to tan phi divided by Fs. This is written here, tan phi m is equal to tan phi divided by Fs. So again you make it as Fs is equal to, so Fs is equal to C divided by Cm, isn't it? Bring Fs to this side and Cm down. Fs is equal to C divided by Cm. And what is this C divided by Cm? It's nothing but Fc value. Fs is equal to Fc. And similarly here Fs is equal to, bring Fs here and bring tan phi m down. So Fs is equal to tan phi divided by tan phi m. And what is this tan phi divided by tan phi m? It is f phi. So you can write it as equal. So in the slope stability analysis, generally the three factors of safety are taken equal.